All right, so yeah, let's move on to contagion. Contagion's great. So, all right. So we go to 4+5. So that's good. All right. Contagion. Okay, so this is a nice big piece. It connects to what we've just talked about. We've talked a lot about things on random networks. We covered some of this in Parks, but we're going to do this in a deeper way here. We had a lot of fun with contagion there, but this is going to be a little more, work out some math. Okay. All right. Again, usual long kind of warm up here. All right. So let's see. We're going to have basic question about will things take off, right? That's a very basic question. So here's something that's broken out in Asia, it's swine flu, whatever it is, or bird flu. Is it going to spread? That's such a big, enormous question for us. So what we want to do here in this course is understand that very well for mathematical models. And we've talked about some of the more complex modeling that's been going on. But you need to, this is the base. Okay, so we'll have kind of global spreading kind of things. We'll talk about network. We'll go to networks, obviously. And then we'll get to these three pieces. So there's a spreading possibility, which is this global spreading contagion. So what's a possibility that takes off? What's the probability that it takes off? So this is sort of just about phase transitions. So can things spread or not? So that's binary. This is what's the probability that they will? So that's a different approach to these. And what's the final size? So this turned out to be a difficult, surprisingly difficult problem. We've talked about random networks being very nice for studying and open to all sorts of analytic possibilities, but this is this piece was kind of hard. So really nice work by Gleason, who's at the University of Cork, and we'll get to that. And so that will be sort of this stuff is about eventually, right? So it's spreading. How big is it going to be? That's a great question. We did, as I said, talk about it in Parks. It's a problematic question, but we can understand in these network models. Is quite high. All right, so here are these questions, right? What's probably there will be global spreading? How far will it go? If you change the network in different ways, will it? If things are more, if nodes are more associative, if they're more closed in, if they're more right? How much can you change things, right? So there's the network itself, and then the spreading mechanism. So there are very different kinds of spreading mechanisms. Have different behaviors. And of course, what if we have many seeds? All right, basic types of spreading, generalized random networks. Right, so this is going to be very sort of general kind of, so generalized networks, generalized spreading mechanisms. Very sort of arbitrary. Okay. All right, so we have this node. It's uninfected, but it's got some infected neighbors. And in some sense, then its connections coming out of it are uninfected. Right? It's not transmitting anything with respect to some particular disease. And so this is an interesting problem, right? So there's memory potentially. This is usually not put into models. We have some nice stuff on generalized contagion. I could put that in there. A very natural, important thing about the real world is that there are obviously lots of things are spreading at once. Usually when it's a big disease spreading around the world, we worry about that. For social stuff, they're usually spreading against each other, right? So stories about Justin Bieber or whatever, they're competing for your attention with stories about, the poor or something, something that maybe you should be thinking about, right? So there's that's more common. Of course, diseases are all sort of in some big ecology as well, but usually when there's a dominant one spreading, we tend to worry about how it's going to work. But diseases can interact with each other too in really complicated ways. Okay, so it turns out that took a long time to really think about properly and analytically. So we tend to think about one thing spreading against the background of everything else, if you like. So we have nice things for random networks. We can think about these pretty cleanly. If you have strong local branching structures, then in your network, then you can really concentrate on that process or that aspect, right? So success, you can think about this node was previously uninfected. There's an infected edge coming in, meaning that it's coming from an infected source. Then it's potentially infectious to everyone else that it's connected to. If it fails, then these are all off, right? So either on or off. So our simplest question is for random networks is whether things will spread, and either you're in the game or you're out. This is the simple thing. You can have probabilistic stories as well. All right, so you've got a network, you've got some contagion process. What's the here's the question. This is a binary yes or no question. Can things spread? Is this thing liable to explode? And so you can answer that more simply and more plainly than also equally, but more important, more in-depth questions like what's the probability? All right, so let's do that. So we're going to do this for random networks, which we've just explored with generating functions, and I'll show you how they will help later on when we try to think about some more complicated things. So we're going to have R is going to be this gain ratio, which we'll talk about. What's the gain ratio in this thing? So typical kind of thing, you get exponential runaway if the gain ratio is greater than 1. If it's less than 1, things have to die out. If it's at 1, then you're at some sort of dangerous border. Okay, so given you have one infected edge in the system, someone's infected, one of their edges is infected in a sense, what's the expected number of new infected edges that will begin? And we'll have different B's later on, but I'll give it this kind of notation now. So BK1 is probably that a node of degree K is infected by a single infected edge. So this could be BKJ later on. Right? So you might have J of your neighbors are infected. You have K friends, you have J neighbors who are infected. Well, it's probably you become infected. All right. But for random networks, for things to spread, because it's a pure branching thing, it has to be by one neighbor. It has to be one neighbor, because you are not going to be getting connected to it by many others. Right? So if you think about the start of it, where it spreads out initially, it's through a pure branching tree. So the initial people who get infected, it has to be through one person. All right. Okay, so we know some of these things. So let's try to calculate this for a generalized random network with this process, which is pretty general, right? So there are, in principle, there's a number between 0 and 1 for every class of node of degree. So classes are degree. Nodes are in classes by their degree, right? So, so that's a fairly general kind of thing. But we'll make it more general. All right, so first piece is, we'll stitch this together. So the first piece is probably that you connect to a node of degree K. So this is our QK, actually. All right, so we connect to it. We've talked about this, but okay. So we jump on an edge. Jump on an edge, we run along an edge. What's the probability that this character here has a total of K friends? Right? So QK equals K times PK, and the normalization is the average degree. Okay? All right. So that begets K minus 1 new infected edges, if it's successful. So probably you hit someone as K friends. This is how many new nodes that are infected, or new edges that it would be infected. And this is the probability that it works, right, that this takes. So we're trying to figure out what's the expected number of new edges. Right? So this is the probability that your infection works. It's probably that you hit someone of degree K, and that's how many you'll get. On the other hand, you can think think about hitting the same, right, that's the same type of node. You get 0 outgoing infected edges with this probability. Right? So it would fail. So this is, you know, this is an expectation of this quantity in here. And if you add these things up, we get we're exploring the full probabilistic range. So this is a 0. This whole thing is a 0, just to be complete. So is this all right? But it's useful to break it into these 3 pieces to see how it works. And that's our global spreading condition. So this got to this pretty easily. So it's greater than 1, things take off. So if you hand someone a piece of K, so this is network, this is the disease. So you can spread these, you can break it into these 2 pieces, see it as these 2 pieces. A lot of stuff we talked about in POX was the problem of trying to not separate these things. Right? This is some, this is a random network, but this is the essence of how people move around or how things interact in this system. And then this is a property of the disease itself. Now, it's absent all sorts of other complications like how networks actually fit together, social networks work, or if these are animal networks, whatever it is. Yes, we're talking about random networks. There's also all sorts of behaviors, that are enacted as soon as a disease starts to spread, but that's not what we're worried about. Very simple stuff. Okay, so a couple of things. So we can say, well, let's set b to 1 for all k, and then this just goes away. Then we have this beast, and we've seen this before, right? So this is now, if you look at this is a k minus 1k. So that's really the average of kk minus 1 divided by k. This is the condition for a giant component, right? We figured out. And it had this somewhat odd property if you go back and look at what we did, which was that this naive thing might be, well, it's the average k times average of k minus 1. Right? So that would be one way to think about it, but it's actually the average of both of these things. And so things with a high second moment, parallel size distributions, this explodes, or it's very large, and this is always greater than 1. So the scale-free type networks are always super good. All right, it's just a giant component condition, so that's cool. A couple of other things. So we could just have beta, we just have a simple thing. So it's just a probability of failure independent of the degree of the node. So it doesn't matter if you're connecting to Oprah Winfrey, who's your buddy, but also has lots of other friends, or your friend who has just you as your friend, which is a bit sad. They have the same chance of you infecting them. So that's pretty silly. You're on Twitter and you send a message to Bieber. It's like you retweet it. It's probably Bieber, as does your mother, right? So, okay. So imagine that scenario. Obviously, it doesn't work like that. So we've got a beta greater than 1. So this actually is just the beta is just a constant. So we can just pull this out. Right, so we really have this is what's happening. So 1 minus beta would do not transmit the edges. It's like having a, so you have the same kind of giant component transition. It's as if the critical degree is, critical average degree is moved. Right, so here's this is just the S1. So this is the so average degree of 1 is here. 1. And then so we will have this kind of thing is happening here. So this is 1 over beta is where the transition happens. Actually, this is a nice little problem. You can think about the degree. This is the same as saying, let's just fail edges, right? Which is a classic problem for not just networks, but more originally from percolation type models where you just fail, you have some structure and you just fail some pieces. It could be a hexagonal lattice and you just fail things, whatever it is. Square lattice, you fail things. So that's known as bond percolation. Either the bonds being on or being off, whatever you have in the frame it. Of course, networks are full of bonds. So you get an induced degree distribution, right? So there's the underlying network, and then you fail things on top of it, and you can write down the modified degree distribution. You can write down its modified generating function, because you would love to do that, which is a nice fun thing to do. Okay, so there's a little extra piece. Right, so generating function in fact is this. So this is the new order distribution actually has this nice feature. So when beta is 1, this is 0, and this is just 1 times x. So it collapses back to where it was because all of the because everything's in the game. When beta is 1, it's a success. That's right. Good. Okay. Okay. All right. Lots of other things. Now you can think about. It's just a little warm up. You can imagine this probability of infection depending on K in complicated ways. Yeah, so there's naturally an asymmetry as soon as you do this, right? So that it depends on the ending node. Right? Doesn't matter who you are, it depends on. So now it depends on Oprah's degree and your friend's lack of other friends. And it could be that this goes up with K, right? I mean, just thinking very generally about it, that's probably unlikely. Right? More likely to infect Oprah than your friendless friend. Could it go up and down? And it could be some sort of weird function of K, maybe. Probably not. It could go down, which makes sense, right? So this is more of the Oprah is less likely to listen to you than your sad little friend. And so this is sort of a basic kind of, sorry about your friend. A simple kind of social contagion. Right? So it sort of makes sure that's sort of roughly where we should be looking. So more well people are how to do things. All right. So moving away from the very simple thing of beta equals 1 and beta is not 1, then a big constant, we get all sorts of things. So here's an example. Okay, it's a reasonable thing to play around. It's just sort of toy things. So let's say 1 over K. Right, so the chance of being infected goes down with your fraction of friends. So it's just inversely proportional. That seems sort of okay. It's not bad. And you can imagine 1 over K to the alpha, dial it up and down. So let's stick it in. We can do it. Well, I mean, we have an equation now, right? So we can just test. Again, it's for arbitrary random networks. This PK could be anything. So I'm going to put it here. It's here, right? That is going to start. It's going to cancel this guy. Right, so these two cancel, and in fact this simplifies quite nicely, right? So we can see now this is the average degree comes out the front. What are we left with? What do we get? Take this out the front. This is the sum of a PKK minus 1.
Isn't that just all the total number?
Well, you can think about them separately. It's the sum of KPK minus the sum of PK. Right, there's a 1 times PK.
Yeah.
So this is
The total number of nodes?
nodes.
Sorry, the number. Degree K.
What is it?
Q sub K?
Well, it's the sum of a K equals, it's a number. It's the sum from K equals 0 to infinity of KPK. That is it's the average degree. Yeah. And this guy? So that's 1. I know we're switching between, so if you think there's infinite networks, probably sums to 1, there is no counting of nodes. There's an infinite number of nodes, which is ridiculous.
So
We've done some where we have finite ones.
I have a question though about PK. If we are, we're looking
This thing, yeah?
yeah, if we're looking at global spreading, and we're trying to relate it to like how things are actually spreading. I thought you said, I mean, it's because that even though we're on a random network, we're looking locally and they behave like branching networks, which are more like what we would see in the real world. Is that why we're using this to hypothesize about contagion, or?
Well, I mean, locally there's a lot of branching structures when things spread out. Yeah, it's true. Like the example we showed you with Brockman and Helbing, right, with the idea of looking at cities. I mean, it manifests a branching kind of thing. And it's true of anything that kind of takes off, basically. At least, here's the complication. I mean, social networks are much richer and more complicated. The things they trace out are branching, usually.
Okay, I guess because I was just wondering, like, why, I mean, it's nice that we have this equation, but why would it necessarily be applicable if random networks are things that don't actually occur? But it would make sense if we're looking at
pure random networks don't exist, but ones with arbitrary degree distributions are pretty, that's not a bad approximation to a lot, some kinds of networks. And random bipartite ones are good ones. That we haven't talked about, but they're good too. So it's not bad. It's not a disaster, yeah.
Okay.
But +1 is not any good by itself. No, we're definitely on the side of trying to understand things analytically as a bedrock. This is always the problem. You know, there's stuff you can really understand, and then there's the real world, it's too complicated. So you need to know, you need to have done things right at this level, and then you can move away from that with some confidence as you sort of leap into the madness of reality. Okay. Now, it was a slightly subtle difference. This is actually the sum from k equals 1 to infinity, right? Because when in k equals 1, this is 0. So we have to be a little, wow. We can just get rid of that guy. Yeah, because k equals 0 will be very 1, right? So k equals 1 to infinity. So there's a slight lie I put over there. So we get, yeah. If this is k equals 1 to infinity, and this is 1 minus p sub 0, right? Because we're neglecting that piece. So average degree minus 1 minus p. It's fine here because the k equals 0 doesn't contribute either. Okay, and then we divide it by the average degree, so we get 1 minus this piece over here. Okay, so this is less than 1. It's over some positive number. This is 1 minus a positive number. So this is always smaller than 1. So this kind of thing is unable to spread, right? So that probability is decaying too fast to allow spreading. We're just sort of feeling things out, right? Now, in a sense, the network is up. So there's arbitrary random networks. They're resilient to this kind of spreading process. If its chance of infecting a bigger character dies away like this too quickly, then it will not take off. So that's interesting to know. You don't have to infect the big ones at all, but which is interesting for it to succeed. But this is, at least if it's decaying like this. Okay, true, independent degree distribution, which is also very interesting, right? So there are, that's super cool, actually. All right, so, so here's another one, a very kind of natural toy model, which we'll explore. The Heaviside function, which I always thought, when I first heard about that years ago, I thought it was heavy on one side. But it's Heaviside with it. It's H-E-A-V-I, it's George Heaviside. Okay. So we named it after someone because we couldn't come up with a better name. All right. It's funny that we do name all these sort of theorems and things after random human beings, essentially. It's supposed to be sort of immortal, or outside of the universe, right? I mean, they're pure and magical things that have nothing to do with us, really. we're just discovering them, but we put our names on them.
Also, usually it's the second person that comes up with it that gets their name pinned to it.
Oh, that's right. So this
First
was.
person's always forgotten.
Did we talk about that? The Stiglers. What's his name? Well, I had this. It was. I think the guy's name is Stiglers. So that's his thing. This guy made up for a joke. He said, Here's a feature of science, right? And things in general. Also saying that he made this up. Someone else made up what he made up. Right? So it was consistent. But he called it his own, named it after himself. I think it's Stiglitz. Stiglitz theorem? It's true. I mean, it's true. And there's probably people that we don't even know about who discover things because they never told anyone. All right. So a Heaviside function. So what is this, guys? So it's just a Heaviside function. It's just a delicious little object. It's a switch, right? So usually this kind of thing. So it's on. H of t. And it's 0 here. It's on. It's 1. People like to give it some value there. You differentiate. You get a direct delta function. All right. So this is a bit of a funny way of saying, well, okay, so 1 over k minus phi. So let's have some fraction phi. So, okay, I guess I'm going to write it in a different way. But 1 over k minus phi has to be greater than 0. So 1 over k has to be greater than phi. Meaning k has to be smaller than 1 over phi. So it's actually this means the small guys are in the game. Right, so you might have here's k and I don't know, let's say 0.18. Right, so 1 over 0.18. Slightly greater than 5. So all of these guys would be in. So they're infectable. These ones are. So this you think might not work very well, right? So now we're just going to send it out through the people with no friends. And ignore the big ones. But in some ways this is quite reasonable, right? So this is not a bad kind of model of social spreading. So, someone has 10,000 friends, they hear one thing from one person. But if they hear it from if you've got 5 friends and one friend keeps going about something, I guess that kind of matters because there's only 5 friends.
I was thinking it was more like if you don't have any friends, then you have more time to sit at home and be influenced by just people.
Okay, but that's media, right? So this is going to be about actual humans that are connected. Yeah. So we can have that as well. We can look at that as well. Well, this would be, but the person has 10,000 friends. If 1,000 of their friends start talking about something, then they know that they've got a better sample. Yeah. All right, so let's stick this in. Okay, so here we've got bk1. We're going to stick this thing in, h of 1k minus 5, which is a funny way of saying it's only for small. It's only for small nodes, poorly connected ones. So really, what this is it's 1 up until, and this is 1 over phi, 1 over phi, and then the rounded down, right? The floor of it. So that's the sum contracts, and then there it is. And then so we want that guy to be greater than 1. So that's possible. I mean, there's nothing to say this might not happen. I mean, PK could be balanced in that way. I mean, maybe everyone has 4 friends, right? You have a pure random network where everyone has 4. Not pure. A random network where everyone has 4 friends. Things can spread on that. So this is also there's no probability attached to this. They're in the game, right? So they will just say sure. It's 1 if they have a low enough number of friends. All right. Okay, so this guy. And of course, as we dial this thing, this threshold, we'll call it threshold. As we dial this, as it goes to 1, then everyone becomes more resilient, right? and that should be big R. But when it goes to 0, then everyone's in, right? So we get our contagion condition back again because this goes up to infinity. All right, so that's okay. That's good. It's not bad. So here's an odd thing we'll find. I mean, this is just simple models. We're trying to understand simple models that tell us a lot. And this is a social type of contagion, which is very extremely interesting. So if we fix this phi and we're going to vary the average degree of the network, we'll see actually there'll be a couple phase transitions. Right? So this R is going to pop above 1 and then below 1 as we vary the average degree. There's all sorts of other complications are going to come up later on. Yeah. So there are two pieces. Obviously, when nodes are not connected, right? So at the limit of average degree 0, no one has any friends, nothing can spread. Right? So it doesn't matter what the thing is. So as it gets connected enough, this particular contagion becomes possible. And then once people become connected enough, they become resilient, right? So they become better samplers of the real world for this kind of contagion, right? So if, that's going to be the transition. Okay, quick little recap. We'll get to a network model. We'll get to a nice network kind of model, which is related to this one. So Schelling's model, which we talked about, right, which was a model of segregation. It was in the late 50s and 60s, and it was really just on checkerboards. But he introduced this idea of thresholds, and it's a profound result. So once again, it's the idea that people want to be next to people like themselves, but it's not that strong a bias actually. Well, so that's what he showed. That's what he put in. Not a very strong bias, but people would move, and eventually the whole thing becomes separated and segregated. And the resulting thing looks bad. I mean, it is bad, and it looks bad, and it seems that everyone was a bad character. But in fact, it can be born out of people with not terribly strong biases. So that's it's a dynamical model, as I said, done on a checkerboard of all things. So then you have, inspired by that, Granovetter. This is 78. You should look at this paper. Who introduced just very simple threshold. So this is a complicated one because it's on a physical checkerboard. This is one where it's the media model. Now everyone is looking, not the media model, but some kind of model where you can see what everyone else is doing. So the media might be reporting what the average person is doing. Right? So you're getting some signal from everyone. And then you have a threshold. Okay. There are lots of others, these herding models and so on. This is from economics, information cascades, all sorts of things. This is economists trying to handle the fact that even rational people are behaving somewhat with some sort of Bayesian thing going on, might end up collectively doing the wrong thing, which is disastrous. Okay, so this is my friend Duncan, colleague from years ago, did some very nice work, started on this. Actually, he was a postdoc at MIT when I was a graduate student there. We talked a little bit about it. Eventually P2P and AS. And so it's inspired by this Granovetter model, but it's really just this. It's going to be networks, it's going to be very simple. And so now people manifestly have a limited view of the world. Right? They're on a network, so there's only so much they can see of everyone around them. Okay, network's sparse, or it has KI contacts. It could be a generalized random network, but we'll get a lot actually out of pure. The thing is, again, we get so much out of pure random networks, you have to work on that, because you have to understand what the mechanism is doing. The link, it's undirected, so influence is a sort of unit weight, right? So you are on, you have 10 friends, each of your 10 friends gets a unit of influence about whatever it is that you've adopted. But it's reciprocal as well, and then everyone has some threshold, right? So this can be distributed. This is a slightly more complicated and simple thing I told you before. Everyone can have their own threshold. And again, that will matter, but it turns out that just fixing a threshold for everyone to have the same one gives you, rich enough behavior. You have to understand that first. All right. bit of an odd thing that you're always looking at what everyone else is doing. It's discrete time update, which is very, in all of these kind of simple models, if you're doing discrete versus synchronous, very different things can happen. You always have to be very careful with that in your own work and looking at what other people are doing. And so it's pretty simple. Nodes, they turn on and they stay on if the fraction of people around them that are active exceeds their threshold. Right, so one way to write that is just this is the active fraction divided by the fraction by your degree, active number of friends who are active divided by the total number of friends. If that's greater than your threshold, then you activate, right? So we can put this over here and say AI is greater than, it's a bit funny way to write it. Is that okay? Okay, fine. And it's permanent activation, right? So it's susceptible, effective, to use the epidemiology kind of SIR. All right, so here's a little example of it. Yeah, so in this case, everyone has a threshold of 0.2, so that translates to 1/5. Invert that, you get 5. So nodes that have 1, 2, 3, 4, 5 friends will switch on. Right? So nodes that have 1 friend are a dead end. Of course, they switch on, but they don't transmit. Nodes that have 2 friends, they can help, but in the thinnest possible way. When you have 3 friends or more, then you start to be able to spread it a little. Right? You can help that. You can contribute to an exponential growth that's greater than 1. All right, so A turns on. I know some of you may have seen this, but A turns on because they've got an infected friend, and they have 5 friends in total. Someone was infected back here, so 1 in 5, so they turn on. And the next step, E has 3 friends. The arrows are a bit, it's not really directed. It's just trying to show you how close. So 1 in 3, so they switch on. This is a 1 in 5 case, so they switch on. And then the last one, there was a 1, this is 2 out of 8, so now they switch on. So these ones are harder to switch on. Right? They needed 2 friends to turn on. Because, right, so if anyone who has 6, 7, 8, 9, or 10 friends needs 2. If you have 11, 12, 13, 14, 15, you need 3. Because then you'll have more than 0.2 of your friends up. But, yeah.
I'm thinking of the sum formula with the BK1, and then that's the mechanism. Is there not a mechanism with respect to time instead of with respect to how many nodes you're attached to? Like some kind of...
Yeah, so time is folded into that probability of switching on. So if one of your... I know that's... Yeah.
I was just thinking
if you think about how these models are made. But so for instance, if you can have it's a rigid threshold, so if 2 of your friends are on, you don't switch on, but 3 are on, then you're on.
Mm-hmm.
Right? It's a deterministic thing. Then that's okay. Like time doesn't matter. It just doesn't matter how much time it takes before that happens.
Okay.
When it is stochastic, do you kind of roll the die every time step that you're in contact?
Yeah. So then that's more. So then effectively what that will do is just it's right, and then that will. So there are 2 ways to do it. One is to have a built-in mechanism like that. We're always sampling, which essentially will just put a delay on whether you switch on or not. It'll put a time scale into it and say, well, eventually you'll turn on, and you just look at what's the expected time. If you're sampling from this distribution, maybe it takes you on average 30 samples for you to get a positive signal. And then you're on, right? The other way is to just do that once. And then you only do it again when your neighborhood changes. Another person turns on, you're like, oh, I'm going to update my states. So it's sort of an event-driven kind of thing. So yeah, but you have to think about what people are doing. We'll do deterministic ones, so these things are okay. And certainly time is unfolding. Extraordinarily, the eventual solutions will actually capture the whole time dynamic.
Okay.
Yeah. Like how it takes off. What are the fraction of nodes of type whatever at time t?
Yeah, okay. I guess that's what it is.
It's kind of amazing. That took a few years to figure out. Okay, so the idea is this, think I've given you that. But it was in pops. Okay, so the ones who can turn on, so they're crucial to these kinds of systems. The ones who can turn on with just one hit. So there's still random networks, but this is that's how things take off at the start. But eventually, even though it's still random networks, you will have nodes that are getting 2 or 3 or 4 hits. And we will actually do things inside the giant component, which is really hard and weird. And you think you couldn't do it. All right, so this is a vulnerability condition for a node of degree Ki. It depends on what their threshold is and their Ki. So if they're one of a, okay, so it's simply this. This is the number active, right? So one of their friends is on, the fraction that are on exceeds their threshold, then they turn on. It means they're vulnerable. So this is the vulnerability. So you take your whole network and you color all the ones that are vulnerable on. That's for which this condition holds, you color them all as vulnerable. Look at that subnetwork. And so the main result, and this is not true necessarily as we go on to all sorts of other things, but it is true here. Is that you need to have a global component of vulnerables for the thing to spread. Right, that's be a so-called giant component of vulnerables for the thing to spread in these random networks. So you have to have a bunch of gullible characters connected to each other. That's really what it is.
Yeah.
And you get one of them, and all of them will believe. And then you start to get some who are less vulnerable, and then some who are even less vulnerable, and eventually you get, you might have situations where you get everyone, even the ones who needed, tons of their, needed 7 hits or something. So they're remarkably resistant. Okay, so we have our giant components, or we have our condition. But we're going to think about this a little bit because it has enough structure. So, a bunch of different pieces here, right? So omega means a component. So this is what I'll call the critical mass, or it's the largest component of vulnerables. And so it's in itself a critical mass, right? So, but it's a very special kind of critical mass because if you just you turn someone on in that thing, then it will spread everywhere, and now it's a critical mass. There are other kinds of models of real phenomena where you have to build a critical mass by paying or tricking or doing or forcing people to turn up in a big group. And they're like, oh, we're a critical mass, right? But one person going out, sometimes it works, right? Someone else will join, and someone else will join, and someone else will join. But often dangerous, right? Depending on the country you live in. Good bad, right? So, and these things can be very well organized. So the Arab Spring, which has been complicated in lots of ways, but Tunisia and Egypt in particular, there's a lot of organization before anything happened for many years. Which I feel probably wasn't true of some of the other countries who in some sense try to imitate what had happened. They're copying this. It's like wearing the clothes of Justin Bieber because you want to be like him. It's the insides that matter. Right? Or your favorite sports person. Whatever it is, people try to emulate what they can see. But anyway, countries do as well. All right, so there's this critical, potentially, this vulnerable component in the middle. There's what I'll call a triggering component around it, and so they have little matches here. So these guys aren't vulnerables themselves, right? They might take 10 hits, it doesn't matter, but they're connected to someone who's in here. One of their friends is a vulnerable in this largest component. So if you switch them on first, they would turn on their friend immediately, who would then turn on, well, eventually all these guys would turn on. So there's a triggering component, which is, it includes all of these characters, of course, right? So that's why it includes all of these characters. But it may include some who are non-vulnerable. There's some final size, if it takes off, which has to include all the vulnerables. It might not include all the triggering ones, right? Because they could be very resilient. And then there's the overall network itself. So I think everything is lined up. So the critical component, the vulnerables, is inside the triggering one, certainly inside the final one. And then all we can say about these is the triggering and final have to be inside the overall network. So this is an interesting, very super interesting thing. Okay. And here's to tell you a little more about it. So we're going to understand this in all sorts of good ways. So, yeah, this is from Duncan's original work. This is, Z here is average degree, right? So we're tuning average degree. This is just for Poisson degree distribution networks, pure random networks. So again, very poorly connected, so actually 0, I guess, is here. Things that aren't connected, networks that aren't connected enough, that doesn't matter what the mechanism is, it can't spread. From one, this is one triggering seed, right? So this is the interesting piece here. We're going to trigger it with one. We're going to start with one node, turn one node on, flip one node on. So there are 3 pieces. So this top curve is the final size of the spread. Okay, and actually that's a transition. It's a phase transition. There's nothing after. This is the size of the largest vulnerable component, and this is the size of the, this should be the size of the triggering component, but I know analytically it doesn't have a fit for that. Just a smoothing line. Okay, so the thing that analytically in this paper is able to show what this curve is like, but not this one or not this one. So we figured these things out later on collectively, lots of different people. Okay, but this is a very interesting thing, right? So this vulnerable component can be huge. So you imagine here, okay, average degree is 3. This is a network where, this is a contagion process where nodes up to degree 5 will be infected immediately. Right? They're vulnerable. They're vulnerable. So that's the game. So when we get out to here, there are lots of nodes. This is a huge fraction of the network that are vulnerable. So really a lot. We're not counting the ones that have 0 friends, so there's no vulnerable component. And this is the size of the largest vulnerable component. So there's a huge cluster, 0.8 of them. But as you start off, the vulnerable component and the final size match up because those two, it never spreads beyond that vulnerable component. Right? It spreads through it, but it never gets anyone who needs 2 hits or 3 hits or 4 hits. It just can't connect to them. It doesn't have enough connections. But eventually that starts to depart. And eventually the size of the vulnerable component goes down because out here, out of this limit, now you have nodes with many friends and they're no longer vulnerable. So 2 things are happening, right? One is everyone, in a sense, is sort of vulnerable back here. They don't have any friends. I mean, sort of. But now they start to get 1 or 2 friends. So yes, they're all vulnerable, but they're not connected. Now they're connected, and they get much more connected. But now the problem is now they're starting to get too many friends, and even though the whole network is getting more and more connected, the largest vulnerable component is shrinking, and then it disappears. So now, at this point, though, you have a very interesting issue, which is there's a tinderbox here. Right, there's a little vulnerable component, and everyone else is very connected. Right? So the average degree is going up. There's an average degree of 6. Remember, I've shown you things like hairballs at 4. Right? This is super messy. Everyone's in the giant. It's just one big giant component. And in fact, right at this point, if you hit that vulnerable component at the start, like you seed it there, then it spreads through the vulnerable component, but it actually gets everyone. Essentially, no one is vulnerable anymore, but it gets the whole thing because it gets some 2s and 3s and 4s and spreads, and in fact gets the whole thing. So this is a really interesting kind of system. This is a very dangerous situation. You look at it, you know what your process is, you know it gets the poorly connected ones, you know that's what it's about. I know that everyone looks very well connected, it looks fine, but it has an Achilles heel. And it will explode horribly everyone will explode in this thing. All right, so I think these things say this. Yep. These are the words. Yep. So robust yet fragile, right? We've talked about that. So it's a robust yet fragile thing. Most of the time you poke this thing, in fact, you get your syringe, or you hand out Bieber records or whatever it is. And most people don't get it, but you get a little patch of teenagers who and then everyone is listening to Bieber. Yeah. So it's a funny thing. So ignorance facilitates spreading in this case, right? Here you're not connected enough. You don't know that there's a world. Here you're connected. You know there's a world, and you're like, oh, that's great. And you tell your 3 other friends about it, right? But here you're becoming sort of knowledgeable and a little not jaded, but you're just like, well, that's not. I don't know. That doesn't seem cool, because you're only 1 out of 10, or whatever it is, 1 out of 1. So, as I said, it's just Poisson degree distribution networks. It's understandable. It took us a while to get to these ones, but okay. This is then a picture of those 2 limits, right? So, just above that lower phase transition, you have this. That the vulnerable component is this piece. Here's the whole network. It's the same as the triggering component. It's the same as the final thing. Right. You can either, you just get in here, it goes, and that's it. This, when we move up here, you have a tiny little one. Triggering component is bigger, tiny little tinderbox. But if you get anywhere in here to start with, it just goes boom and destroys the whole thing. So it's an unexpected behavior. This is connected, this should look a little bit like, well, it's reminiscent of what we said when we talked about the average size of finite components, right? That explodes around the critical point. So this is the kind of a critical slowing. Well, that's not the right term actually, but this is how long it takes to get through the network. And you can see it has this feature of things are blowing up. It's simulations, so there's a limit to what you can do. It's blowing up again, so there's that. So bad things happen around phase transition. All right. So, the endogenous mechanism for spreading. Right. So let's play around with this a little bit. I know some of you are saying we're going to go through it again, but here's the threshold, right? So everyone's gonna have the same threshold. And out to a quarter, so that's 1 in 4 of your friends, and then we're decreasing it. So lower and lower threshold means more and more people are in the game. Higher and higher threshold means the more resilient it is. So at least for this kind of network, once you pop off here, nothing can spread, right? So this is a binary cascade condition situation. You get no cascades for out here, cascades in here, and this is the average degree. So we sort of flip the picture that we usually have. So for a given threshold, there's a window, right? Well, there's a range over which spreading can occur, and this window opens up as the threshold goes down, because more and more connected individuals are vulnerable, right? So you can get out to networks that have an average degree of 25 because a lot more nodes are vulnerable. So this is a picture that we had, right? Just on the previous page. This is one slice to connect the previous ones we've had. This is our fraction of vulnerables here. This is our final cascade size. Some example of these networks. And so you get this kind of picture on all of these. All of them have a sharp, this upper phase transition is a horrible discontinuous one. This is a smooth continuous one. You go from no cascades to cascade size of 0, and then slowly going up, and then eventually it drops brutally at this end. Probability of them occurring is going down towards these edges, of course, as well. That's not shown. All right. Okay, so I'm going to connect it to all networks, and then I think we can, which is the media kind of story, and then I think we can come back with the theory next week. That's what we're going to do. Okay, so again, we've got this deterministic response function idea, right? So you're on, you turn on, each individual turns on. That's just what we had before. But now you have some distribution of thresholds in the population. Right? Before everyone had the same threshold. This is, if we want to go out to something where everyone is watching everyone else, now there's no variety in your experience of the world. When we have networks, there is a variety, and that's enough to think about, to be interested by. Now we have to say, okay, let's vary the thresholds to get something interesting. Okay, so a couple of things. So one is we have this some distribution of thresholds, whatever it is. And then we'll call it F. Little f, big F will be the cumulative distribution, standard cumulative distribution. We're going to integrate from 0 to phi star, right? So, and that will matter. So phi of t is the fraction of people who are whatever they're doing, right? Believing at time step t. Right? So that's what we're interested in, how this phi of t plus 1, how does this thing work? Again, this is for a media type situation. You can see what everyone else is doing. There's a clock. Everyone decides to change their behavior every time step because they're teenagers. And so we have, all right, it's pretty simple, right? So the fraction that are going to believe will be the ones that have their thresholds less than whatever the fraction is now, because there's some fraction that are infected. You see it, it's 0.7, your threshold is 0.6, you're like, I'm in, right? And you could drop. You could have been in, and now it's gone down to 0.5, you're like, okay, now. So the fraction that are on at the next time step, this is very simple, it's the integral from the 0 to the fraction they're on now of all the thresholds. So this is then the fraction of, so it's a cumulative distribution. You could put a minus f in brackets, you could do that might. It's possible to have a value there, of course. So, but in general, it's this, okay? So, the fraction that are on it, the next time step is just is this map, whatever it is, it's a cumulative. You're given some distribution of thresholds, it's a cumulative. Map to the next one. So, if you like chaos, you'll be thrilled to see this because this is maps of the interval. Right? Okay. And so all sorts of possibilities arise, right? So here's the individual response function. Here's, say, an example distribution of the thresholds, right, of this point. Right? So this is something where there are very few that are gullible, right? And there are very few that don't adopt. This is where everyone's kind of in the middle. If you integrate that function, you get this shape. And if you then iterate it, so let's say we start with some fraction that are on. So we're going to do this sort of thing again and again. So this is a good example. So let's say, and 0.5 is the fixed point here. So iterate. This is a cobweb diagram. So this is a nice way of doing these iterates of maps of intervals. You haven't seen them. So we start here. Okay, that's our next. That was phi naught. This is phi 1. So we go over here, we figure out what it is, and we come back and plug it in here. And an easy way to do that is actually just to go back to the line. So then you've realized you can actually just go, you can bounce off the thing. So this will actually go to 0. If we start here, you can just sketch out that it's going to go to 1. So this is a critical mass type model. So this distribution makes for a critical mass type model. You have to have a certain fraction on for the thing to then run itself. Right? If you went out and paid people to wear funny hats, right, and we only paid 30% of them, it goes to 0. It's a bad plan. Although you don't know about this thing, so it could have been, it would never have worked. Okay, so discrete time, yep, it's critical mass. This one is kind of the opposite story. So you've got a bunch of true believers here, right? They're totally into it. These ones will take some time to convince. You integrate that thing and you get this kind of form. And the crucial thing is that this integral, this function is great, its derivative is greater than 1 at the origin. this derivative is less than 1 at the origin. So nothing can take off. That's right, exactly. So, boom, boom. So it's an unstable point now, unstable fixed point. Start with 0, nothing takes off. You got to put a little believing in, and then it will spread. But there's a limit. They're like, that's enough. You know, these characters out here, you're not going to get to them. And even if you started, you sent everyone a Belieber t-shirt, right? Like you just totally hammered them with it. Even if you start at 1, that's it, right? We're done. But you just need to be a little bit away from 1, and then it decays back to some stable single state in the middle. Right. Okay. So we've talked about this, but it's very, so, right, collective uniformity does not mean that everyone's the same. It looks like it, of course, because they are now, but it doesn't mean they were intrinsically. And a really big point here is if you change this a little bit, somehow you change this distribution, and you start to move this distribution of thresholds around a little bit, right? It's not that good, believe it or not, you should do it. Like this starts to kind of get pushed down a little bit, then this can eventually go below 0, and it won't take off. Or, you could be at this state, and this line goes like this. Right? Sounds like this, and it's like, no. Say, not even like that, but say this whole thing falls below like that. It's just a tragedy. Which definitely happens to our friends who are celebrities. Okay, so, public mood changes. All right, so but that's just this is invoked to try and not exactly describe, but just sort of understand that these huge sudden things can happen in societies. All right, I'll make this one comparison, and then we're good. I want to connect these two things we've talked about: the mean field model and the network model, because they seem to be quite different. But the mean field model is really an all-to-all network. Everyone is connected to everyone. Think about that. So we're still in network world. The problem is, for networks, we think about one seed because it's discrete, and we think we're going to set off one seed. And we can think about setting off many people, but we'll think about one. With this big mean field model, when we say epsilon, we mean epsilon of some sort of infinite population. So, be a little careful with that. Anyway, this is the picture. And we'll finish with this. Okay, so all-to-all networks are here. And then these random network stories are here. Okay, let me get this right. Okay, so this is the one I was just showing you, for example, for the network story, right? The Dark and Watts' thing. So this is the final size, boom, and this is the size of the vulnerable component. So as we go out here, we're increasing the average degree, right? Average degree is increasing as we go out here. Eventually it goes to sort of infinity, which is the all-to-all network thing. So in some ways, I could put these diagrams around the other way. This, right out here at infinity, is this picture. Because this picture is where everyone is looking at everyone else, and it's a situation where we're using the same, these are using the same threshold distributions actually, so it's connected. This is their threshold distribution. Right, this is little f, you integrate it, you get this big F, and it's a critical mass model. Right? But if we start here, then it goes to 0. So in fact, the weird thing is, when it's an all-to-all network, nothing ever takes off, right, from a small seed. But if you took that all-to-all network and then made it more and more sparse and people were less observant of each other, as you pull that away, you start coming in on this axis here. And eventually you get to a point where actually one seed can make the thing explode. All right, and so that's our critical mass type model, our single stable state model, this one, right? So looking like this. So again, here are our gullibles, here are our resistant people. Boom, 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 goes to 0. It goes to this fixed point. That's the all-to-all. That's when everyone's looking at it. Now, if we start to take away connections, and people can't see each other as much, we start to come in on this line. And it makes sense, right? So in fact, it makes sense. The final size is in fact a half. Right? This is actually starting to match up with with this final size here. So right out here on this limit, everyone's watching everyone else, and in fact, yes, it always spreads from a very small seed. Right out here on this limit, tiny seeds never take off, which matches this story. So they're connectable. They're very different kind of stories, but they're connectable. But then, this is going back from here to putting it on a network. It's like, okay, most of the time you get to half the population. That's what happened in the mean field case. This is completely different to this. Right? You're coming in, you're like, yeah, nothing takes off, nothing takes off, nothing. Right? It's just like the mean field thing. It's like, oh my god. And this is really weird. So, yeah, super interesting thing. So, okay, so we're going to go to getting to the final sizes. We'll get to some generating function things as well, and but it's a lot of fun. But it will spread out back out to all sorts of possible kinds of spreading mechanisms. So it's weird. Okay. Yeah, there's a lot with Contagion. So we'll do one. I'll run you into the ground, but not too much. Not too much. But it's really good fun stuff, and there's a lot of understanding to come out of these simple models. So, and you can't really talk about anything complicated until you kind of know these things. So, okay, plan. So we'll sort out office hours for next week, and we'll be back here on next Thursday. We'll bring more food, and you can. All right.